Hello, welcome to this lecture. In this lecture, we'll be studying about tangent plane of a surface. So suppose you take a regular surface in R3. So corresponding to each point, we'll assign a plane that will be tangent to that surface. So that plane will be called tangent plane. And the vectors lying on that plane will be called tangent vectors. Okay, so let us begin. Okay, so let us start with a regular surface in R3. So let S be a regular surface in R3. So let me draw a picture. So suppose this is my surface. So this is my surface S, and let us take a point P in this S. Okay, so what do you mean by tangent vectors at the point P to the surface S? So what you do? So in order to define tangent vectors at the point P, so you take all possible differentiable curves passing through the point P, and then you take the tangent vector of that curve at the point P. Suppose this is my curve alpha, and alpha 0 is equal to P. So this is my alpha prime 0. So this is the tangent vector. Okay. So let me define. So by a tangent vector, so by a tangent vector at the point P belongs to S, uh, we mean, so we mean alpha prime 0 of a parametrized differentiable curve alpha defined on this open interval minus epsilon to epsilon to S, such that alpha 0 is equal to P. Okay, so this is my definition of tangent vector. So if I take any other curve like this, and if I take the tangent vector here, if this curve is beta and beta 0 is equal to P, so I'll just take the velocity vector P prime 0. Okay, so this collection will give you a set of vectors at the point P. Okay, so this is my definition of tangent vectors. Okay, so now let us prove this proposition. Uh, so this set of vectors, okay, so it will form a plane, and if this plane, if you transfer it to origin, it will be a vector space of dimension 2. So let me draw this tangent plane here. So the set of all tangent vectors at the point P, it will form a plane. Okay, and if you translate this plane to the origin, so you'll get a plane here. So this will be my vector space. And this is my tangent plane at the point P. Okay. All right. So now let me do this proposition. So I have taken this S to be a regular surface. Okay. So I'll get a surface patch containing the point P. Okay. So let uh, sigma U to S be a surface patch uh, such that P it belongs to sigma U and U is an open subset of R2. Okay, so U is an open subset of R2. And so the okay, so maybe I'll just write this thing. The vector space spanned by the tangent vectors okay so is of dimension 2. Okay, so the vector subspace spanned by the tangent vectors, it is of dimension 2. Okay, and so d sigma q of R2. So this coincides with the uh, vector space of of tangent vectors with the subspace vector subspace of the tangent vectors. So what is this q? So q is sigma of, so where sigma of q is equal to p. Okay, so this we are going to show. So again note that, so you have a map sigma from this u. So u, it is an open subset of R2. So this is my say q. So you have a map sigma from u to this surface. Suppose this is my surface and sigma of u, it will be something like this curved surface patch. So this is my sigma of u and we have this point P here. So P is equal to sigma of q, and what I am doing, so I am taking the tangent plane here. Okay, so the vectors corresponding to this tangent vector, so this will form a vector space. So it means that if I translate this plane to origin, so this will give you a vector space of dimension 2. Okay, all right. So now, so what is the proof of this? Okay, so now let us take any vector in R2 starting from this Q. So, or let us take any vector. So let us take, so B be a vector in R2. And now let us take this curve, let gamma t equal to t b plus q. Okay. So there exists an epsilon greater than 0 such that because this U it is an open set, so such that gamma of minus epsilon to epsilon is contained in U. Okay, so what is this path gamma t? It is the straight line passing through Q with velocity vector v. So this is my curve gamma, which is a straight line. So gamma of 0 is equal to Q, and gamma dot 0 is equal to B. So this vector, B, it is a vector which starts from origin. Now you can just translate it. So you'll get a vector which starts at Q. Okay, or in other words, so this vector starting from Q is parallel to the vector B passing starting from the origin. Okay, so this is my curve gamma, and now I can take a small interval. Okay, if you restrict this gamma on this small interval, it will lie in U. All right. uh, so now, so what you do, so you apply sigma on this curve gamma. So, so let us take, so let beta of t, so this is equal to sigma compose gamma t. Okay, so then, so this beta, it is a curve from this, beta is a curve from this minus epsilon to s, and so what is beta 0? So beta 0 is sigma of gamma 0, which is equal to sigma of q equal to p. And what is beta prime 0? It is it is equal to uh, the following. Yeah, so it is equal to d sigma of q evaluated at the point gamma dot 0 or gamma prime 0. Okay. Okay, so this is equal to d sigma of b. Okay, so now let us take, so let w equals to b prime 0. Okay, so which is now equal to d sigma q of P. Okay, and beta, it lies on the regular surface passing through the point P, and beta prime 0 is equal to W. So this implies that, so W is a tangent vector at P to the surface S. Okay, and so what we have shown that, so d sigma q of R2, okay, uh, is a subspace of, or subset of, set of all tangent vectors at P. Okay, all right. So now let us take any tangent vector at the point P. So so W be any tangent vector at the point P, okay, to the surface S. Okay, all right. So now again, let me draw this picture. So this is my surface S, and I have this point P, and I have some tangent vector. So this means that, so we'll get some curve beta such that beta prime 0 is equal to W. Okay. So then, so there exists a differentiable curve beta defined on some small open interval such that beta of 0 is equal to P and beta prime 0 is equal to W. Okay, all right. So this S, so this is my regular surface. So this P, it will be contained in some surface patch. So this will be sigma of U for some U sigma. So I have this U, and I have a map sigma from U to sigma U. So this U, again, it is an open subset of R2. Okay. So there exists a surface patch U sigma such that this P is contained in this sigma U. Okay. All right. And now what you do, so you define this B. So let us take, so let alpha to be equal to beta, sorry, sigma inverse compose beta. Okay. So if I do this thing, uh, so then, so there exists epsilon 1 such that 0 epsilon 1 is less than epsilon. So, uh, so this beta, so this alpha, it will be defined on this small open interval minus epsilon to epsilon to uh, yeah, so to your U. Okay, so if I do this thing, and then so alpha will be defined here. So alpha of 0 will be equal to P. Okay, so alpha of 0 will be equal to P. And so d sigma sorry, alpha of 0, it will be equal to your q, and d sigma q of alpha prime 0 or alpha dot 0. So this will be equal to beta prime 0, which is equal to w. Okay, so this is easy to show. And so note that this sigma inverse, okay, so this is differentiable in the sense that, so this we have done in the earlier class. So I can get an open neighborhood of this P in R3, something like this. So this is an application of inverse function theorem. So I can get hold of a differentiable function from this U cross R to R3. So that is my F, okay? And so F is a local diffeomorphism. So F is local diffeomorphism. And if I take F inverse uh, restricted to this slice, okay, so if I take F inverse restricted to this sigma u, it will be equal to your sigma inverse. So, and F inverse, it is differentiable map, okay, so in that sense sigma inverse is also differentiable. Okay, so therefore, so this alpha, so will be also differentiable. So then alpha is differentiable. Okay, all right. So therefore, we have proved this proposition. So we have shown that d sigma q of R2. Uh, so so what we have shown that d sigma q of R2 is equal to the set of all tangent vectors to the surface S at the point P. Okay, and d sigma q, it is a linear map. Okay, so d sigma q, it is a linear map, and d sigma q is injective. Okay, so this implies that dimension of this subspace d sigma q of R2 is equal to 2. Okay, so therefore we have proved the proposition. So that is the set of all tangent vectors, it will form a subspace of R3 and it will be of dimension 2. Okay, all right. And now let me make this remark. So while defining tangent vectors, we have done it through only taking differential curves on the differential, this regular surface. Okay, it does not depend upon the surface patch. All right. So the plane, the tangent plane, or the yeah, let me write in this way. So the plane, this sigma q r2, uh, which is equal to the set of tangent vectors at P belongs to S. Okay, so uh, does not, or maybe I'll just add one more thing, that the plane d sigma q r2, maybe I'll just erase this. So this plane d sigma q r2, which passes through the the point P equal to sigma of q, does not depend on the parameterization sigma. Okay. So let me again state this thing. Suppose you have the surface and this is my point P, and I have a tangent plane here at this point. Okay. So the vectors corresponding to this. So if I take any point, let us take any point x, y, z in this plane. So this B, it will be nothing but equal to x, y, z minus this P. So this vectors forms a subspace of dimension 2. Okay, and this plane passing through this point P, okay, this plane, it is called the tangent plane. Okay, all right. So now, what will be the basis of this set of tangent vectors, this vector subspace of tangent vectors? What will be the basis of this? Okay. So, basis of the tangent space. Okay. So now let us take, so let S be a regular surface, and let us take a point P belongs to S. Okay. So now let us take, so let U sigma be a surface patch such that, so this P, it belongs to sigma of U. Okay. All right. So let me draw this diagram. So sigma is mapped from this open set U to this surface patch. Okay. So now, so for a small interval, so I can take the straight line passing through Q, which is parallel to x-axis, and that small straight line, it is a subset of U. Okay. Okay. So in other words, so what I want to say is the following. So let us take the this orthonormal vector. So let us take E1 to be 1 comma 0 and E2 to be equal to 0 1. So sometimes this E1, it will be also denoted as del U, and this will be denoted as del V. So this is just notation. Okay, and now let us take, so let alpha 1 t to be equal to, so t 1 comma 0 plus the point q. Okay, so there exists epsilon greater than 0, epsilon 1 greater than 0, such that, so this t or alpha 1 of this minus epsilon 1 to epsilon 1, it is contained in this U. Okay, and let us take alpha 2 t to be equal to t 0 1 plus q. Okay, so similarly there exists epsilon 2 greater than 0 such that alpha 2 of minus epsilon 2 to epsilon 2 is contained in U. Okay, and now let us consider this curve. So let beta 1 to be equal to beta 1 to be equal to sigma compose alpha 1 and beta to be equal to sigma compose alpha 2. Okay, yeah, so again if I come back to this picture, so suppose this is my alpha 1. Okay, this is just a straight line passing through q whose velocity vector is 1 comma 0, this unit vector, and if I map it to the surface with the help of the map sigma, so we'll get a curve. So this is my sigma compose alpha 1 which is equal to beta 1, and again for this perpendicular line alpha 2, so I'll again get a curve which I have called to be beta 2. Okay, so this alpha 1 and alpha 2, okay, so these are perpendicular to each other, and the velocity vectors, so alpha prime 0 is equal to e1, alpha 2 prime 0 is equal to e2. So e1 and e2, so these are my, so is a basis for R2. Okay, and now if I apply d sigma q on this alpha 1 prime 0, so this will be equal to uh, this beta 1 prime 0 d sigma q of this alpha 2 prime 0. So this will be equal to beta 2 prime 0. Okay, so so this will imply that, so this beta 1 prime 0 and beta 2 prime 0, so this forms and forms a basis for the tangent space. Okay, so this will form a basis for the tangent space. And now notation. So E1 I have denoted as del del U, E2 I have denoted as del del B. Okay, and now d sigma q of del del U, so this will be denoted as del sigma del U, and d sigma q of del del B, okay, it will be denoted as del sigma del B. Okay, so del sigma del U, so this at the point Q, and del sigma del B, yeah, so this will be at the point P, and del sigma del B at the point P. Okay, so now what we have, if I draw the picture again, so this is my point P, and I have this tangent vector del del U. So if you want this, you can denote it as del del u at the point Q, del del V at the point Q, at the point P, at the point Q. This is my point Q. And I have another orthogonal tangent vector del del V at the point Q. And this map sigma, it is there. So this is my surface patch. Suppose this is my surface patch. So I have this two curves like this. So whose tangent vector, it will be like this. And this is my del sigma del u at the point P, and this will be del sigma del V at the point P. So this two tangent vectors, so this will generate this tangent plane at the point